Hello everyone, welcome to this presentation on our paper Efficient Exact K-nearest Neighbor Graph Construction for Billion-Scale Datasets using GPUs with TensorCores at SAS 2022. This is a collaborative work by my supervisor, Professor Cho-Li Wang, and me. Nearest neighbor search is a fundamental building block for various applications such as recommendation system and image search, and also data mining. With the rapid growth of dataset sizes, accurate NNS becomes impractical. Some studies propose approximate NNS techniques that accelerate NNS with index. This index can be roughly categorized into four classes: hash-based, condition-based, tree-based, and also graph-based. Among them, graph-based methods have shown great potential as they can better express the neighborhood relationships in high-dimensional space that suffers the curse of dimensionality. Many state-of-the-art graph-based indexes are based on KN graph. In an exact KN graph, every point connects to its k-nearest neighbors in the same dataset. For query point Q, its KNs are found by traversal of the KN graph. KN graph limits the number of neighbors of each point to k to avoid too many neighbors, which reduces memory usage and accelerates the query. The advantages of KN graph for almost all graph-based indexes are at the expense of high construction time. While most tree-based and condition-based index can build in nearly linear time complexity, building KN graph-based indexes incurs very high computational cost. The most time-consuming part is to build the initial KN graph, consists of distance matrix calculation and topk selection. So it is essentially the whole graph NNS. KN graph construction can directly use the NNS implementations, which separate the computation into two standalone kernels. It is easier to optimize the performance of standalone kernels, especially for the distance matrix calculation kernel, which can use the efficient general matrix multiplication implementations provided by some BLAS libraries, for example, cuBLAS. However, it incurs two unnecessary global memory access for the distance matrix. The first kernel computes the distance matrix and stores it into this memory, and the second one loads it back for topk selection. The space complexity of the distance matrix is O(n) squared, which is in Oak scale for billion scale dataset. It takes a significant portion of the overall workload to transfer such a large distance matrix. Moreover, the large device memory requirement itself also hurts the performance. For billion scale datasets, the dataset is divided into several batches and processed in mini-batch manner. The distance matrix occupies a large amount of US memory, which could have been assigned to the dataset, so it leads to more batches and thus higher data transfer overhead. To solve the problem, we can execute topk selection on the fly with distance calculation, or more specifically, fuse them into a single kernel. On-the-fly topk selection is much more challenging than kernel fusion in the deep learning area, which usually appends an element-wise function, for example, an activation function after another kernel, such as convolution kernel. Activation function usually only requires several arithmetic operations, while topk selection involves various operations, occupies many on-chip resources, and also incur many branches. Fusing the state-of-the-art matrix multiplication kernel and topk selection kernel may not result in an efficient KN graph construction algorithm. The key feature of fly KNG, our method, is to co-design the two algorithms to optimize overall throughput. So we design our method FlyKNG, a KN graph construction algorithm accelerated by TensorCores enabled GPUs with on-the-fly topk selection. It deploys the distance matrix calculation to TensorCores and also customized topk selection algorithm for the data layout of TensorCores. The key feature of FlyQNG is to co-design the two algorithms to optimize the overall throughput, and we will discuss them in detail. We first briefly introduce how we deploy the distance matrix calculation to TensorCores. The distance matrix calculation computes the distances between any 2 points of dataset. It can be represented by matrix multiplication and the most widely used distance metric, such as dot product similarity, the cosine similarity, and the Euclidean distance. The dot product similarity between 2 points pi and pj is defined as this. So the distance matrix of the whole data set can be written as this matrix multiplication. As it is essentially matrix multiplication, it is natural to use TensorCores, the specialized hardware unit for matrix multiplication to accelerate the distance matrix calculation. Additionally, the cosine similarity is defined as this formula, and the squared Euclidean distance is this. So the squared Euclidean distance is the same as the squared L2 norm of the 2 points minus 2 times the dot product similarity. And also the cosine similarity is equivalent to the dot product similarity for L2 normalized point. So the time complexity of L2 normalization and computes this is OND. It is much lower than that to compute this, which is ODN square. With trivial processing costs, the distance matrix calculation for the cosine similarity and the Euclidean distance can also be represented by matrix multiplication and thus accelerated with TensorCores. Finding top k elements of an array need to go through all elements of the array. The distance matrix calculation of FlyQNG assigns the same rows of the distance matrix to the same warp. It may not be the best choice for the matrix multiplication itself, but it avoids topk selection suffering high interwarp communication cost and thus benefits the overall throughput. The matrix multiplication algorithm of FlyQNG has a different performance optimization objective, as it does not need to store the output matrix and has an irregular workload assignment imposed by on-the-fly topk selection. We customize the matrix multiplication algorithm for FlyQNG based on some comprehensive discussions of its performance optimization objective. The most important parameter are tiling sizes. Because of the workload assignment, algorithm 1 does not partition the computation along the D dimension. Each warp iterates matrix B with a loop in batches and multiply it with the same tail of matrix A. Intuitively, keeping the tail of matrix A in shared memory can avoid loading it multiple times. Moreover, it short-circuits the impact of the tail size along the n dimension. As the computation is not partitioned along the D dimension, matrix B does not involve data reuse from the perspective of each thread block. A small tail size along the n dimension does not hurt the throughput. It allows matrix A to occupy more shared memory. A thread block can process more points, which reduce the total number of thread blocks and thus global memory access. The small tail size along n dimension also increases the probability of successfully topk selection pruning, and we will discuss this later. The workload of each warp is a small regular size matrix multiplying a tall and skinny matrix. It is a best practice to use the outer product computation style rather than the common inner product computation style for this kind of matrix multiplication to reduce the shared memory access. However, it needs to occupy extra registers to hold the intermediate data. Registers are critical and limited resources for our algorithm, which also execute topk selection. The topk elements are stored in registers, and the compiler usually trades extra register usage for a higher ILP. instruction level parallelism, especially for kernels whose streaming multiprocessor (SM) whose SM occupation is bounded by shared memory usage, while the outer product style computation can improve the performance of conventional tall and skinny matrix multiplication. It may not be a good trade-off for flaky NG. Then we came to the top key selection part. We adopt the partially sort style method to compute the top key element. The first thing we need to solve is how to sort the output of TensorCores or fragment in NVIDIA's terminology. The conventional way is first storing the fragment into shared memory or global memory in row major or column major with these official APIs. The disadvantage of this method is occupying shared memory, which impacts the data reuse or distance matrix calculation. Also, shared memory is still slower than registers and requires funds to guarantee the access order. Thus, we need to find a method to sort the output of the TensorCores directly. This figure shows the data layout adopted by NVIDIA's TensorCores. The left side shows the MMA matrix multiplication and accumulation in the programmer's view. The matrix loading and storing functions, or APIs, assume the matrix stored in global or shared memory in either column major or row major layout. On the other hand, the underlying data layout of the output matrix stored in 8 registers, which is shown in the right side figure. The output matrix is divided into 4 8 times 8 tails, and every 2 vector registers store such a tail. For example, R0 and R1 hold the upper left of the output matrix, the upper left tail. The official document does not specify the data layout, and it may change in future TensorCore architectures. However, a similar tailed major layout, so we name this data layout as tail major. A similar tailed major layout will still be adopted because of the best practice of tailed matrix multiplication and the design principle of TensorCores. This algorithm 2, shows the algorithm that sorts the values stored in tail major layouts entirely with registers. It achieves the least number of intra-warp data shuffle. No matter how many registers are sorted, algorithm 2 only needs one intra-warp data shuffle for Bitonic sequence construction here, and 2 shuffles to make the Bitonic sequence into a sorted sequence. It is line 6 and line 7. Even though the algorithm seems long and complex, it is a very efficient regular kernel, or in other words, all instructions are actually statically determinable at completion time. All loops can be unrolled, and the compiler can freely schedule instructions to improve LLP. And also, all threads execute the same instructions at the same time, which indicates that no warp divergence is incurred. It is advantages inherit from the Bitonic sort family algorithm. This figure uses an example to illustrate how algorithm 2 works when n equals to 1 or for n equals to 4, step by step, where R is the register's name and T is the thread and thread ID. For tail major layout, every 4 thread sorts an independent sequence so that this figure only shows 4 threads, while the warp size of most NVIDIA GPU's microarchitectures is 32. Figure A to figure C are the steps to construct the Bitonic sequence, and after building the final Bitonic sequence, the for-warp sorts the Bitonic sequence into a descending sequence, as shown in figure D. And reverse one can be sorted simply by reversing the comparator. The instruction for every compare and swap in each step are also shown in this figure. All threads execute the same instructions at the same time, which indicates that no warp divergence is incurred. And also, we can see that there is no need for dynamic indexing, as we have the register name for every step. So we can entirely use registers to do the sorting, and there's no need for dynamic indexing. This algorithm shows the detailed algorithm for the on-the-fly topk selection built with the algorithm proposed here. It is one of the selection by partially sort algorithm, while the conventional Bitonic sort algorithm is an offline algorithm. Our algorithm can process streaming data that comes in batches, such as the distance matrix computed by TensorCores. The key is to maintain the invariant that the top key elements of the same distance are in descending order. So this figure shows the steps of algorithm 3 in each iteration. It first sorts the distances computed by TensorCores into an increasing sequence. Then the new computed distances form a Bitonic sequence with a current or old top key element, which is in decreasing order guaranteed by the invariant. It then selects the top key element from the Bitonic sequence and sorts them in decreasing order to guarantee the invariant. We can simply merge the Bitonic sequence to guarantee the invariant. However, it is noted that only the first key element of the descending sequence need to be kept. So algorithm 3 explicitly performs the first pass of the sort Bitonic line 8 to line 9. Actually, the top key elements have already been founded after line 9, but they form a Bitonic sequence rather than a sorted sequence. It still needs to be sorted into a decreasing sequence for the invariant. While the distance calculation is unavoidable for brute force KNG construction, the top key selection can be safely pruned. If a distance is smaller than the smallest top key element seen so far, it cannot be a top key element, and thus is skipped for top key selection. GPUs are SMD processors, single instruction multiple data processors, and Bitonic selection needs the input size to be a power of 2. In order to avoid warp divergence, a warp skips top key selection only if the whole top or bottom half of the computed distance in an iteration does not need to go through top key selection. So line 4 in this algorithm, the tiling strategy of flat KNG allows a small n, as we discussed before. So and it also does not hurt the data reuse. So it improves the probability of successfully warp green top key selection pruning. We evaluated FlyKNG on NVIDIA RTX 3080 and also A6000 and A100 GPUs. These three MP architecture-based GPUs have various shared memory capacities, global memory throughputs, number of tensor cores, and also number of CUDA cores. The experiments are conducted on 4 high-dimensional datasets ranging from million scale to billion scale. All values are in bfloat16 format, a data type commonly used in machine learning areas, which preserves the approximate dynamic range of float number. So this table lists the specification of the 4 datasets. SIFT1B contains 1 billion SIFT descriptor, Scala invariant feature transform descriptors. So 1 FCC 100M and Deep1B are open source datasets of CNN descriptors. So for ImageNet 21K, we compute CNN descriptors as the one before last layer of a ResNet, whose dimensions are then reduced to 128 with PCA. Among them, Deep1B and SFT1B are billion-scale datasets, which occupies more than 100 gigabytes of storage. This is the software specification, and we evaluate 4 exact KNG construction algorithms. The baseline is the NS implementation in CUML or FAISS library. They share Morse code for NAS, so we denote it as CUML FAISS. Simply fuse the distance matrix calculation kernel and the standalone topk selection kernel that use shared memory for topk selection. The topk selection algorithm is selected from the popular standalone implementation that rely on shared memory for topk selection with some preliminary test. So FlyKNG is the algorithm proposed in this paper, and FlyKNG no skip is the same as FlyKNG but does not enable warp-grained topk selection pruning. Actually, even the baseline achieves 4.91 times higher throughput than simple fuse with standalone kernel on RTX 2090 and A6000. It incurs two unnecessary global memory access for the octa-scale distance matrix, but still shows a much higher throughput, as the two kernels are highly optimized for standalone usage. On NVIDIA A100, the performance gap between the baseline and simple fuse is less significant, which is 2.79 times throughput than on the other two GPUs. The shared memory of each SM can be configured to 164 kilobytes on NVIDIA A100, while that for NVIDIA RTX 3090 and A6000 is only 96 kilobyte and 100 kilobyte respectively. With larger shared memory, the shared memory usage of topk selection has less impact on the data reuse or distance matrix calculation. FlyKNG no skip is the KNG construction algorithm proposed in this paper, but without topk selection pruning. Compared with UML, it achieves 2.49 times speed up when k equals to 16 and 1.28 times speed up when k equals to 64. FlyKNG no skip selects topk elements on the fly with distance matrix calculation. It does not need to store and reload the large distance matrix, which occupies a considerable portion of the overall workload of CUML. It is noted that the execution time of FlyKNG no skip significantly increases with k. Without topk selection pruning, every iteration of the algorithm needs to execute topk selection. When k is large enough, the KNG construction time of FlyKNG no skip will longer than CUML. However, such a large k is not common for KNG construction. With topk selection pruning, FlyKNG shows 4.67 times and 2.47 times throughput on average compared with CUML and FlyKNG no skip. Moreover, the execution time is not sensitive to the number of neighbors, or k. When k equals to 64, the KNG construction time is only 9.55% longer than that when k equals to 16. For real-world applications, a point usually has a sufficiently high similarity with its k nearest neighbors, but a low similarity with most points of the dataset. Otherwise, if all points have very high similarity with others, NS is meaningless. Thus, FlyKNG will prune many executions of topk selection. The warp-grained pruning strategy is much more coarse-grained than others. However, FlyKNG's tailing strategy for distance matrix calculation improves the probability of successful pruning. The space requirement of the ImageNet 21K dataset is only 5.6 gigabytes. The whole dataset can be stored in this memory when constructing KNG for ImageNet. The gap in the performance between COML and the FlatKNG non-skipping is less significant on ImageNet 21 than other datasets. On NVIDIA A100, COML achieves a slightly higher throughput than FlatKNG no-skip. However, for other test cases, FlatKNG no-skip still shows 2.11 times speed up compared with COML on average. These two figures show the breakdowns of the execution time of COML and FlatKNG with the sampling of warp scalar states. It shows that COML suffers very serious long scoreboard stalls, which indicates that the warp spent much time waiting for scoreboard dependency on global memory operations. For distance matrix calculation, the latency of global memory access can be very hidden. However, the standalone topk selection kernel does not have enough arithmetic operations. Even if highly optimized, it still cannot totally hide the latencies incurred by loading the distance matrix from global memory. Adopting standalone kernels allows sophisticated optimizations for each kernel, especially for the distance matrix calculation kernel, but it does not result in high overall performance. On the other hand, FlatKNG only suffers 0.22% long scoreboard stalls. However, it also causes a low ratio of MMA instruction and shared memory access. Some studies propose to use the outer product computation style to reduce shared memory access. FlatKNG does not adopt it as it requires extra registers, which are also heavily used by the topk selection part of FlatKNG. It is a necessary expense, the MIO store for on-the-fly topk selection. As future work, we aim to implement FlatKNG on other AI chips with TensorCores, such as AMD GPUs and also Huawei Ascend processors. We are also interested in integrating FlatKNG into other approximate KNG construction algorithms. So in this paper, we presented FlatKNG, a KNG construction algorithm accelerated by GPUs with TensorCores. It adopts on-the-fly topk selection and co-designs the distance matrix calculation algorithm and topk selection algorithm to improve the overall performance. So the distance matrix calculation considers the data communication costs and the pruning strategy of topk selections, and the topk selection try to have as least impact as possible on the data reuse of distance matrix calculation. On billion scale data side, FlatKNG achieves 4.67 times speed up compared with the state-of-the-art approaches COML. Thank you for listening.